So we've worked several strut problems now, which basically gives us the conceptual foundation to skip forward to chapter 6 in your book. And in a separate video, I'll actually show you some example pictures of tractors, loaders, excavators that have this kind of mechanism on them. And this is chapter 6 again in your book, which in chapter 6 you'll do trusses and you'll do machines. And this is the back end of a backhoe, and this is a pretty complex looking problem. But if you notice, there's a bucket here that pivots at B. This is a hydraulic cylinder, CE. And look, there's a link AC, a link CD, and then this hydraulic cylinder. And so this hydraulic cylinder will contract, which will pull C to the right, which will cause this bucket to pivot upward about B. Or this hydraulic cylinder will elongate and push at C and basically rotate the bucket downward or counterclockwise around B. If you just focus at that particular joint right there at C, that's joint equilibrium. That's what we're doing right now. Now, there's other things going on here, but for what we're doing now applies to this guy right here. And the reason these are common mechanisms for backhoes and excavators and tractors is that using two links, AC and CD, allows the flexibility for the bucket to pivot around B. And then having the distance between C and B, having some distance there, gives this hydraulic cylinder a moment arm about B. And so this bucket has a weight that acts downward through its mass center, and it produces a moment about B, a turning action. And by pulling or moving this hydraulic cylinder away from B, it gives it more of a lever arm about B that gives you reasonable forces in the hydraulic cylinder. And so it's a very handy way of accomplishing that motion. But you know enough now in particle equilibrium to analyze this joint. And so if you draw a free body diagram of joint C, and if we assume that this hydraulic cylinder is pulling with a 500-pound load here, what are the forces in AC and what are the forces in CD? Well, all three of these forces are concurrent at C. In other words, they intersect at C. And so I can use particle equilibrium at C to analyze these two guys. And there's just two unknowns, so I can write two equations, so I can solve for those guys. I need their directions. And so I need to make an assumption as to whether CD is acting down to the right or up, and which direction AC is acting. And that can actually be a little bit difficult. But if we basically rotate the coordinate system and call this X prime and Y prime, and if we mentally sum forces in the Y prime direction, if FC is 500 this way, then FCD has to act this way for this guy to be in equilibrium in the Y prime direction. Once we figure that out, then we can sum forces in the X direction, just in the X direction. And well, actually, we can rotate a coordinate system around this and call this X prime and Y prime. And then we can sum forces in this Y prime direction. And if this is pulling this way, then this has to be pulling this way. It turns out these guys are actually, well, no, they're not, yeah, they're 90 degrees. Turns out these are 90 degrees apart, but that's not, we're not taking advantage of that right now. But basically, if you sum forces in the x prime, or basically perpendicular to this guy has to act this way. And so that's kind of the mental thinking you can do to get the directions of these forces correct. If you don't get them correct and you solve the problem, if they come out negative, then basically means that they act opposite of how you assume them. But again, that's one of the reasons for the free body diagram is you commit to a direction of this unknown. You write your equations based on that assumed direction. And then if they come out negative, then you go, oh, okay, they go the opposite way. But you have a record of your thought processes that confirms it for you. So this is my free body diagram. So I could sum forces in the rotated coordinate system, but I'll just do x horizontal and vertical. And so in the vertical direction, I have negative sine 40 FCA plus FCD sine 50 is equal to 0. And in the horizontal direction, to the right to be positive, I have minus FCA cosine 40 minus FCD cosine 50 plus 500 is equal to 0. If I set this up in a matrix form, negative sine 40 is this guy, which is the same as cosine 50. Sine 50 is this guy, which is the same thing as negative cosine 40 down here. On the right-hand side, I've got a 0 and a minus. When I bring this guy over here, it's a minus 500. I can solve this matrix using my calculator. I get FCA is equal to 383 pounds. And he's pulling, so he's in tension. And I have FCD is 321.4 pounds. He's pushing, and he's in compression. So this is a Chapter 6 machine problem. This is theoretically a hard problem, but you know enough now in particle equilibrium to be able to solve this problem.